degrees, and we need to calculate the force of friction acting up the slope. So if it's at rest, then we know that the forces acting down the way are going to be balanced by the friction force going up the way. So if we find the size of the force acting down the way, then we know that that is going to be what the size of the friction force acting up the way is going to be. So here's the object, and that object is experiencing a weight force, and the weight force acts straight down towards the centre of Earth, and the weight force is mg. Now, this object, because of the presence of the slope, can't accelerate in the direction that that weight force is acting. So what happens is it slides, the force is acting down the slope, it wants to slide down the slope. We know in this case friction is stopping it, but a proportion of this weight force down is acting down the slope. And so what we really need to do is we need to work out what proportion of this weight force acting straight down is actually acting down the slope, because that's what matters to us. And then we can say, well, the friction force is going to be the same size as whatever proportion of this weight force is acting down the slope. So the force acting down the slope is, and there's I suppose different ways of doing it, but I suppose the cheap way of doing it is to say, well, if we're starting in this direction and we're wanting to see how much is acting in that direction, we are crossing an angle that isn't known. Now I know you could work it out, 90 minus 30, but we're crossing an angle that we don't know, that hasn't been given. So if we're crossing an unknown angle, we use sine. So the force acting down the way is going to be mg sine 30. If you don't like that, then you could find a triangle, so make that sort of triangle like that, and say, well, what you're wanting is the opposite, and we've got the hypotenuse. So, and then you could say, well, the opposite is the sine of the angle times the hypotenuse. So there'll always be a triangle you can find, or you could just do that cheap method for resolving. And remember, when you're swinging through a particular direction, if you don't know the direction you're swinging through, if you don't know the angle you're swinging through, then it's sine. However you want to do it, force acting down the slope is mg sine 30, 5 times 9.8 times sine 30, which is 24.5. Newton's first law deals with things which are at rest and moving at a steady speed, but in this case it's at rest. So like I said before, we know that forces are balanced, so the friction force up the way must equal to whatever proportion of this is acting down the way, and we found that, so the friction force acting up the way is going to be 24.5 newtons. So here's a similar situation. We've got a 5 kilogram mass on the slope. It's being pulled up the slope at a steady speed by a rope, and we want to find the tension T in the rope. Well, again, it's a situation with Newton's first law, because we're going at a steady speed. So again, if we find the proportion of the force acting down the slope, we know that T is going to be the same size, because it's a Newton 1 situation, because the thing is being pulled up at a steady speed. Now, I've talked about this before. The proportion of a 5 kilogram mass acting down the slope, we find the weight first, mg, then we say, well, it's mg sine 30, so T up the way is the same as the proportion of the weight acting down the slope, which is mg sine 30, and just carry on as before. But what happens if, okay, different numbers, we've got a block on a slope, we've got 500 newtons acting up the way, and the question is saying, well, calculate the maximum acceleration of the block. So what this is implying is that the upwards acting force is quite a bit bigger than whatever proportion of the weight force will be acting down the slope. So to complete our force diagram, we need to find what proportion of the weight force is going to be acting down the slope. So again, the pure amount of weight is mg, and that acts vertically down the way. We know that this angle is going to be 40, and we want to know the proportion of this mg which is acting down the slope. So it's going to be mg sine 40. We're turning through an angle we don't know, so it's sine. So mg sine 40. So we've got this force going up the way and it's bigger, we've got this force going down the way and it's smaller. So fun equals ma. Working out the overall effects, which is what fun is, it's the big one, take away the small one, equals mass times the acceleration. Solve this however you want to solve it, but the answer comes out to be 2 meters per second squared. So, experienced weight. Newton's third law is this idea of action and reaction. So, if you remember the example we gave in Nat 5, if you punch a wall, then yes, you are putting a force on the wall, but the wall is putting an equal and opposite force back on you. So it's the idea of what you actually feel is the reaction force or the support force. Contact forces come in pairs, and what you feel is the reaction force. If you stand on an upturned plug on the ground in bare feet, then you certainly feel the upwards force from the 3 prongs of the plug, and arguably it's not a support force, but you certainly feel that upwards force. So if you are standing on the ground, the reason you don't fall through the floor is, yes, you have your weight force acting down on you from the planet, but then there's also a support force acting up on you from the ground, I suppose, from all the electrons on the ground repelling the electrons on your feet. We don't need to go into that, but your weight force is balanced out by the support force. So the support force, which is what you feel, is the same size as your weight force. You're at rest, and normally the support force is the same size as the weight force. And the upwards experienced weight force, that's the upwards force, that's what you experience, that's why it's called experience force. That's also what bathroom scales feel and show you. Okay, so normally you feel what your actual weight force is, and if you stand on some bathroom scales, normally the bathroom scales show you what size your actual weight force is, because although they show you not your actual weight force, they show you the upward support force, because most of the time the upward support force is the same size as the downwards weight force. Most of the time, if you're just at rest, the scales accurately show the weight force, even though what they're actually showing is the upward support force. If, however, you are in a box, call it a lift, and you are accelerating upwards suddenly at 1.2 meters per second squared, what are you going to feel there? What is the upwards reading on the scales, or what is the pupil's experienced weight force if you suddenly start accelerating up the way? Well, if we're accelerating, then Newton's second law is F equals ma. We need to be dealing with that, and let's call this upwards force, let's keep calling it the support force. If the whole system is accelerating, there's going to be an upward support force. So it's upward support force minus your weight force acting down the way, which is mg, is mass times the acceleration. Support force upwards, which is what you feel, minus the mass, which is 50 kilograms, times g, which is 9.8, equals mass, which is 50 kilograms, times a, which we're told. The support force upwards, which is what you feel, is 550 newtons. Now, if you compare that with what the pupil feels when they're not accelerating, if you just do W equals mg, well, W equals mg, the weight force on this person comes out to be 490 newtons. So that's what they normally feel, because normally the upward support force, as we saw on this previous slide, is the same size as the downwards weight force, so they normally feel 490 newtons. But if the support force suddenly has to increase to achieve that acceleration, then that's what they feel. They feel the 550 newtons. The weight force, 490 newton stands, remains the same, but you don't feel the weight force, you feel the upward support. So if the upward support force is increasing, that's what you feel, and you feel heavier. And if you've been in a lift which suddenly starts accelerating upwards, then you'll know that that's the case. Alright, projectile motion. What even is a projectile? A projectile is an object moving unsupported in a gravity field with no other forces acting on it. So some examples of projectile motion: you throw something forward, or you're up on a cliff and you throw something out the way, or you drop something vertically down the way, or there's a satellite in orbit around Earth. So these are all things, these are all objects with no other forces acting on them other than gravity. A Top Gun missile is, shot from a fighter jet. That is not projectile motion because that's got the thrust of a rocket engine on. And similarly, a rocket, when it's launched and it's going upwards, that's got continual thrust from its rocket engines, and so that's not a projectile. Once the burn is finished and your satellite is in orbit, then that is projectile motion. Anyway, when something is moving with projectile motion, you've got this distinctive curve. So let's say this is this situation. Somebody's lobbed something forward. You can think about, although the speed is going up in that direction, the velocity is going in that direction at that point, you can decompose it into, you can think about, well, what proportion of that velocity is going horizontally, what proportion of that velocity is going vertically. And if you do that, then at every given point in a projectile's flight, and this is the same for every single projectile, what you'll see is the proportion of the velocity acting horizontally is always exactly the same. It maybe doesn't look the same size how I've drawn it, but the horizontal bit is always the same size, but the bit which changes is the vertical component of the velocity. So at the point of maximum height, for example, and something's thrown forward, then there's no vertical component at all. And then as it starts vertically going down the way, the vertical component of the velocity gets longer and longer and longer. So you can always split motion up into, well, whatever components you want to split it up into, really, but at higher we always split them up into horizontal direction and a vertical direction. So horizontal and vertical components. Somebody once said to me, think of it as like the axis of a graph. So at higher we always use the along axis and the up axis, the y and x, but actually you could choose any funky axis you wanted. Anyway, horizontally there's no forces acting. Remember this thing, definition of a projectile, where the only force acting is gravity. Well, gravity is a vertical force, so horizontally there's no force acting. Well, if there's no force acting, Newton's first law says, well, the thing will be going at steady speed. Vertically, there's gravity acting. So if gravity is the only force acting, or the force of gravity or the weight force, that's an unbalanced force acting because it's the only force acting. And so if there's an unbalanced force of gravity or a weight force, then there's an acceleration in the direction of that unbalanced force, which is down the way. So the acceleration due to gravity is 9.8 meters per second squared. And if there's an acceleration, then that means the speed is changing. If the ball is thrown up, then the reason that the upwards components of velocity get smaller and smaller and smaller is that there's the downwards influence, the downwards acceleration. Remember, a good way of thinking about acceleration is influence. The downwards influence means that the vertical component of velocity gets less and less and less and less and less, and then after the 0 points, the vertical influence, the vertical acceleration means the vertical component of velocity gets more and more and more. So, when you're asked to calculate stuff about the flight of a projectile, you need to be sure whether the question is asking you about some kind of horizontal quantity or some sort of vertical quantity. So if it's asking you for horizontal range, for example, or even just range, then you'd have to realize that's a horizontal thing. Now horizontally, because there are no forces acting and it goes at a steady speed, we can only use the constant speed formula. Distance equals speed times time, or s equals ut if you like. So if this is the thing which is thrown forwards, you've got to be careful that if you're dealing with the horizontal axis, the horizontal question, then you've got to deal with the speed on the horizontal axis. Now we're not given the speed on the horizontal axis, we're given the speed, the starting speed, at an angle of 40 degrees. So let's swing round to get to the axis we want. Now if we are crossing a known angle, then we use cos. Again, if you wanted to turn that into a triangle, then you could get this side of the triangle by